Hi, welcome back to my whiteboard. I'm Kevin Dorma. This is part 2 of the control series, and we will look at two different tuning strategies for PID controllers. First, we need to describe how a common process behaves mathematically. A common process is temperature control for a heat exchanger. The objective is to hold the outlet process temperature on set point by adjusting the flow rate of the hot oil. We can do a plant test to see how the outlet temperature behaves when the control valve is opened 1%. The outlet temperature will increase and level out in the following manner. This is a first order process. There is some dead time, and it is assumed to be 5 seconds. The first order time constant is the time needed to reach 63% of the ultimate temperature rise. The time constant is assumed to be 30 seconds. The process gain is the change in outlet temperature for a unit change in valve position. We will assume it is equal to 1. This is the process that we will use for demonstrating two different tuning strategies. The two tuning strategies that we will look at are modified Ziegler-Nichols and Lambda. There are lots of other recipes that are similar to Ziegler-Nichols, but we will use the modified form because it is common in most auto tuners. The modified Ziegler-Nichols method is less oscillatory than the classic method. I am not considering tune by feel as a strategy because there is no defined objective. Both Ziegler-Nichols and Lambda have defined objectives and recipes. You should be able to find the mathematics for Ziegler-Nichols and Lambda in any process control textbook. Let's look at a simulation example where our temperature controller is tuned using the Ziegler-Nichols recipe. Here's a block diagram simulation of our temperature control example implemented in Scilab. The process is modeled as a first-order transfer function and a constant dead time. The PID controller is set with a gain of 2.7 and an integral constant of 0.16, which is the gain divided by an integral time of 17 seconds. The first disturbance is a change in set point at 100 seconds and a load disturbance at 300 seconds. And I've added a small amount of random noise to make this a bit more realistic. Let's see how this responds. The change in set point is managed very quickly with some overshoot and maybe a tiny bit of oscillation. The load change is also managed very quickly. This is one feature of Ziegler-Nichols. The objective is to match the change in set point or eliminate disturbance as quickly as possible at the expense of potential overshoot and oscillation. Notice the valve position in blue. There are large swings in the controller output to force the process to change as fast as possible. Ziegler-Nichols is designed to manage disturbances as fast as possible at the expense of some oscillation. Lambda methods are different. Here, we choose the response time as a design parameter. We can set the response time to be as fast as necessary, but as slow as we can get away with. We will look at 3 examples. We will start with a response time of 20 seconds, then we will look at 5 seconds to show a faster response, and then 40 seconds for a slower response. This is the same model as before, except with the lambda tuning constants. Let's see how it responds. The set point change is managed more slowly than Ziegler-Nichols. The majority of the set point change is obtained in the 20-second response time that we specified. There is no overshoot or oscillation on the temperature. The load change is also managed in about 20 seconds and shows no oscillation. Lambda methods are designed to manage disturbances with no oscillation in the measured value. The valve position does not change nearly as much compared to Ziegler-Nichols, and there are no oscillations in the valve position. For lambda methods, the objective is to manage a set point change within the specified response time with no overshoot on the process variable. This also avoids oscillation in the valve position. Now, let's retune the controller to target a response time of 5 seconds, which is this simulation, and we'll run it. With a target response time of 5 seconds, the set point change is starting to show some oscillation, and the valve position has a fair bit more overshoot. And let's change the target response time to 40 seconds with this simulation. The closed loop response is slow and predictable over 40 seconds. Lambda methods are designed to respond in a non-oscillatory manner. Well, non-oscillatory as long as we don't try to tune them too aggressively. Targeting a specific response time for a control loop is a simple technique to ensure that different control loops do not interact or fight with each other. This will be discussed in Part 6. To summarize, there are two general strategies for tuning a PID controller. One is to tune the controller to respond as quickly as possible. The other is to specify a desired response time. Speed comes at the expense of oscillations in the controlled variable and the control valve. We need to consider how important oscillations are to the process and other control loops that may interact with the one that we are working on. A successful control strategy is one where all of the controllers work together as a functional team. Next is Part 3, Process Gain and Temperature Control. I'm Kevin Dorma. Please visit my website at www.kevindorma.ca. Take care.